Now, we are going to interview John Morton, who is a professor in nanoelectronics and nanophotonics at the University College London. His research areas are deeply in connection with quantum computing, for example, the transfer of quantum information.
What type of qubits are there and what types of qubits am I interested in? So I think one of the really fascinating things about quantum technologies is that you can take almost any quantum system and represent information inside it. And people have looked at taking optical photons, states of atoms and ions, and magnetic properties like spin, either of electrons or nuclei, and use all of those states to represent quantum information. Some of the states that I'm most interested in are electron spin. They occupy a middle ground in many ways between these different systems, and they interface well with each other. They interface well with the charge degree of freedom, or with light, with microwaves. And that can be used in different ways. In particular, I'm interested in electron spin states within semiconductors and within silicon especially. That's largely due to silicon's important role in the semiconductor industry today. Very advanced techniques that are available for fabricating silicon devices, building on the decades of experience that we have in purifying silicon and refining methods for patterning. So eventually, although quantum computers promise to revolutionize the IT industry, they could end up using a very similar materials platform, which is silicon. Advantages and disadvantages of the types of qubit I work on. Electron and nuclear spins within silicon devices have various advantages and disadvantages. For example, it builds on the very large body of experience that we have working in silicon, thanks to decades of work in the conventional IT industry. That means that silicon is one of the most pure materials that we have today, and that we really understand advanced techniques for fabricating them at very small scales. I'm particularly interested in looking at the states of individual dopant atoms within silicon, such as phosphorus or bismuth, and using the states of those atoms to represent qubits. But that poses huge challenges, because although silicon fabrication is very advanced, we're talking about engineering the states of individual atoms, and that's a length scale that goes beyond the, say, 10 or tens of nanometer processing that typically happens to get today. So one of the challenges will be combining the advanced fabrication methods that are used in the conventional silicon industry with the requirements to control the states of individual atoms. Another challenge is that these devices typically need to work at very low temperatures, just a fraction of a degree Kelvin above absolute zero. And although there are some very well-established methods using dilution refrigerators to place quantum devices at such temperatures, that does mean that you won't be carrying such a quantum device in your mobile phone on a day-to-day basis. But with the advent of things like cloud computing, people are becoming more and more used to sending problems on their mobile phone to be solved at some distant server, and not really caring about the infrastructure that's around that server. And so in the same way, even though an advanced computing device like a quantum computer may be sitting within a dilution refrigerator in a specialized facility, it could be accessed remotely from anywhere in the world, and that user would effectively be impervious to the fact it was operating at low temperature. How are qubits made? So there are various ways to produce the silicon devices that are used for silicon qubit technology. One approach is to start, in a sense, from a blank slate using specialized fabrication resources in a university, and begin to draw one's ideal device of what a qubit should look like, taking dopant atoms that are placed into the silicon and designing, using advanced lithography techniques, the infrastructure around it to control and measure it. And that way you can make 1 qubit and 2 qubits and build up slowly, eventually hoping to map out a path towards a large-scale device. Another approach that I'm quite interested in is to start at the other end and look at the devices that the CMOS industry is making today. For that reason, we have a project with a CMOS research foundry looking at some of their current FinFET transistors and looking at whether those same transistors that are used in classical information technology can be operated in a different voltage regime, cooled down to low temperatures, in order to exhibit quantum characteristics. And that provides a different direction of which to approach the problem of using silicon industry to produce silicon quantum devices. Difference between electron and nuclear spins, control and measurement. So one of the attractive things about using the states of dopant atoms within silicon is they contain at least two interesting degrees of freedom which can be used to store quantum information. This includes both the electron spin of the electron which is bound to the dopant atom and the nuclear spin which sits at the very heart of the dopant atom. Both of these are magnetic and they have different spin properties that can be used in different ways. For example, the electron spin can be manipulated on a timescale of a few nanoseconds using microwaves, and its state can be measured out using a variety of demonstrated techniques. On the other hand, the nuclear spin, although it's slower to manipulate and harder to measure, has extremely long coherence times, and so it remains in fragile quantum superposition states for times as long as minutes when the electron is present and hours when the electron has been removed from the donor. When do you expect the first real quantum computer? So it's notoriously difficult to make predictions about future technologies. There's a famous quote in the development of the conventional computer about a predicted worldwide market for 3 computers. Nevertheless, we can look at past history in the development of the conventional computer to try to steer us in terms of how quantum computers will be developed and over what sort of timescales. For example, you can go back and look at the first patent for the field effect transistor, which forms the basis for current CMOS circuits. That took place in the 1920s. And this was followed 27 years later by the demonstration of the first individual transistor in 1947. Then there was the integrated circuit connecting these transistors together into one device in 1958, and then eventually the first microprocessor was sold at the beginning of the 1970s. And so we can just map that timescale and apply it to what's been happening in the quantum computing industry. The first ideas, the patent or the birth of the concept of a quantum computer occurred in the 1980s. And then the equivalent of the first transistor, the single qubit devices, indeed followed about 27 years later in the mid-2000s, depending on which degree of freedom was being observed. That would mean that we should expect the quantum integrated circuit to appear sometime around 2018, and given the recent developments, especially within ion traps and superconducting qubits, we seem on track to see things that certainly look like integrated circuits occurring on this timescale. But that means that we need to wait until about 2031 for all of these developments to reach a point where the quantum version of the microprocessor becomes commercially viable. The question is, what would I do with a quantum computer? The universal quantum computer represents the most complete computing device which we can conceive of based on the laws of physics as we know them today. They're, in a sense, the more complete version of the Turing machine, incorporating the laws of quantum physics as an extension of classical physics. Already some specific applications for quantum computers have been conceived in areas such as factoring large numbers, sorting large disordered databases, and new applications are emerging in areas such as optimization and perhaps even machine learning. However, one of my main motivations is the application first predicted by Feynman in the early 80s, which is that of quantum simulation, taking the fact that accurately simulating quantum mechanical systems, which ultimately materials and chemicals and molecules at their ultimate level are all quantum mechanical, that's a hard problem for classical computers to solve. And so if we can come up with advanced universal quantum computers that could potentially radically change the way that we're able to make predictions about how molecules will interact and how materials will behave, which could have a big impact on a wide range of areas in science.